Good morning. We just pop into the game of the day. You knew this was coming sooner or later because I really actually wanted to to show you Genshin at a particular point in the course. I can't remember exactly what it was. Um, I think it was Oh, excuse me. Characters are talking while I am. I think it was when we were talking about making characters and things like that, because this is a game with like 50 characters, so there's a whole lot of stuff in it. But today we're talking about mapping, and mapping is all about giving extra surface detail to objects that might not otherwise be there. And Genshin actually has a fair bit of that. Like, if we look at, there's a bit where it's a little bit sort of shiny. Check out these cobblestones where I am here. See them catching the light there just around, just below my character, just off this lamp here. Ooh, watch the day-night cycle happening in real time. So if you see the light reflecting off these cobblestones, there is this kind of appearance, this idea that the cobblestones have actual geometry. You know, they've got a rounded edge on them and the light is reflecting off them. But like, watch as I get closer to parallel to the plane, you can actually kind of see them. You can see them sticking up out of the ground just to the right of my character's feet.
Where I'm from, if we didn't keep moving, we'd
And then watch this.
Literally.
You can actually see this effect. The closer I get to flat, the less these cobblestones appear to be popping out of the ground in any way, and the less they appear to have any kind of curvature over the top or corners or geometry or anything like that. And the more they reveal their true structure. And the true structure is just a really big flat polygon that has some information on it, and it has that information that's on it is information that we're going to use to give it a kind of a view and lighting characteristics that make it appear like it actually has edges. So what's really cool is when you're just running around and you're not thinking about this, the cobblestones, like here we've got the same effect. The cobblestones reflecting light, and the gaps between the cobblestones not reflecting light and stuff like that is something that we just assume, we just accept. We look at it and go, yeah, of course, that's what cobblestones do. And we don't realize is we're being completely tricked by a series of surfaces placed like on what is otherwise geometry-wise a really boring flat plane. And so this is what we're doing today, is we're looking at some of the techniques we can use to map things to flat surfaces to get these kinds of effects. Alright, so I'm not actually playing Genshin today. I was just looking at a small piece of ground in the town, because that's like, that's kind of like what happens when you study graphics too much, is you get caught up in this. This is why I'm showing this game, because this happened to me while I was playing the game. It's like, I could be out there, you know, like, I don't know, exploring the world, fighting monsters and all that kind of stuff, but instead I was just like, hey, look, hey, it's, like, I knew, because I know these techniques, I was pretty sure that was going to be a flat plane, but look how nice it looks, even right down to here. You can really see the idea. Like, look at the, oh, I need, wait, a pointer. Look at this one here. You can see how you actually can and can't see parts of it. The only bit that gives it away is that while it can obscure other parts of the floor, it cannot obscure my feet. So even though at this angle it looks like this particular cobblestone is sticking up out of the surface, and it is obscuring parts of the ground behind it, once I move it to a certain point where it should be covering up part of my feet, then it gives it away. That's the only time that this surface kind of gives away the truth of the fact that it is not 3D, and that thing's not actually sticking up out of the surface the way it appears to be. It's all just a trick of the rendering of the flat surface and the lighting and things like that to make this look like it's sticking up out of the ground when it isn't. So I think that's the key. So right there, so you can see that that cobblestone really looks like it's sticking up out of the ground. But then when you look at it with my foot there has just kind of punched straight through it. So it's a really interesting kind of thing. And we're going to look at some of those ideas today. So let me just quit out of Genshin. And go to our slides for today. Oops. Genshin has this hilarious habit. It's one of those games. It's just like, hey, why don't you keep playing me forever and maybe put a whole lot of money in as well. It's one of those games. So like every time you quit, it it takes its time. It waits like 3 or 4 seconds and then pops the window up again. So in other games, when you quit, the game just disappears and you go off and do something else. But this game gives you enough time to go off and start like either typing in stuff or clicking on other things, and the window just pops up in front of things. I've had multiple times where I've left the game and then I've gone onto Discord or something else and just started typing to someone. And if I press the space bar exactly when that window pops up again, it relaunches the game. It's pretty funny. It's interesting the techniques that games will use to kind of, I guess, force you to interact with the game as opposed to like just doing it through pure entertainment value. Okay, so let's get into it. What were we doing last lecture? So last lecture, to remind you of what we were doing a variety of different advanced lighting techniques, and I didn't really have the time to go through in like, extreme excruciating detail into any of these techniques, but I think hopefully I've given you enough information about each of these so that you can say, oh, okay, that's interesting, or that's like, I want to look up that further. I want to see more detail on how that works. So um, a lot of these are just bits and pieces that are used. Some of them are used more than others. One of them in particular, Blinfong, the lighting technique for what I would call a correction of Fong specular lighting. So it takes out one of the awkward artifacts of specular lighting in Fong lighting. That's one that we're just going to use from now on because it's a very, very easy conversion of our lighting algorithm from Fong to Blinfong. So that's one that we're just going to throw in, and then we're going to be using that in our specular lighting calculations. The other ones less so, so they will take a little bit of effort, and they're the kinds of things that if you want to, you could play around with. I think if I remember correctly, I think maybe Matt was putting that in this week's tutorial, was throwing gamma correction. I can't remember if that was the case. It was this week or next week that because it wasn't super difficult to do, he was just going to throw it in. He was just going to allow the frame buffer to run as an sRGB frame buffer, which is not that hard to do. That's a one-liner if you assume that everyone's monitor is a 2.2 gamma. So you might see that as well, because a lot of things like light mapping is much harder, but there are a lot of things I'm going to teach you about, and I have before, that exist kind of as OpenGL one-liners. Like they're part of the library and someone else has written it already, so you can just go in and use it. Yeah, so those are some things. They're not, obviously not the only things. I didn't choose like every add-on that's ever been made to Fong lighting. Just a series of them that were quite easy to cover, I guess, in half an hour each. There are other things, I think, and I did mention things that that I thought would be quite important. and shadows and reflections are two of those, and then we're going to do them next week. I'm going to do reflections more than shadows because the technique is easier to understand with reflections, and then shadows, if I decide we have time to do it, we will, which we potentially will, but we'll see how we go. Whereas these were techniques that sort of sat on their own. I mean, there's other things like what we're doing today, which is maps, and I want to say adding geometry to a surface, but it's not geometry. It's technically not geometry, as you saw in that demo that I showed at the beginning. It's not actually geometry, but it's the idea of geometry. Exactly the same way that when we're using textures, what we were doing is we were giving the surface more detail by changing color across the surface without necessarily having to add vertices and triangles or anything like that to your to a particular object. So part of that's going to come in today as well. So what are we covering today? We're covering lighting maps. So these are, as I was just saying, additional surface details, and they're going to help make lighting effects happen. And it's a little more than just that, but they're going to help lighting effects happen in the same way that textures help color and rendering happen. So when we're working with a texture, what we're going to get is the surface is going to get extra detail based on what colors are in the texture. But we can do more than just colors. There's a whole lot of stuff that goes into the lighting equation. Things like normals and also different textures for different types of light. I mean, it's not even really different types of light. I would actually say it's different properties of the material itself. And so we're going to be doing stuff like that today, like adding different maps to different objects and having a look at the differences that they make. And this shouldn't be too hard. I mean, especially because I'm not really going to go through all the maths by hand in one particular form of this, which makes it very difficult. But the benefit that we're going to get out of this is one that I think that you'll understand reasonably well because we've done it with textures, right? It's adding additional complexity, in a sense, to geometry that doesn't have it otherwise. So should probably just go straight into textures layer, because if I talk about it in that regard, it's easier to then go on to the other maps. So what is a map? And so instead of going straight in to what a map is, I'm going to start with a little bit of a revision. So textures are a type of map, and they're usually stored in a material. So what we would often do is we would say this object has this material, and the material might be made up of several different maps. The texture is usually two-dimensional, and it usually stores color data. So we can think about it as a two-dimensional array, and each element of the array is a 3D vector. Well, actually, it's a four-dimensional vector, which is RGB alpha. Probably should have just called it a four-dimensional, because there's other places in this where I call it a 3D vector. But you know, a lot of the time we're only concerned with the RGB, but plenty of the time also we are concerned with the alpha. So 3D, 4D in terms of the color vector, they're interchangeable. We'll use either one. We can tell where the texels, so the individual colors from the texture, we can tell where they apply to an object based on their texture coordinates. So every vert in the object has texture coordinates, which is a mapping. So it's a mapping between world space and texture space, in a sense. So what we're going to do is say, if this texture is going to go across this triangle, and the triangle's like, you know, at some weird angle in world space, because, you know, especially in any kind of real-time dynamic situations, you're never really going to tell what alignment a triangle is at any particular point in time. So it's like, it's here at this angle, and the texture just gets slapped onto it. And so it gets mapped onto it by saying, this texture exists in 2 dimensions somewhere else. So it only has 2 coordinates, a u and a v. But what we can do is by mapping those coordinates to verts, we can get the colors of that texture to appear somewhere in space aimed in a particular direction, right? So that's the mapping. That's why they're called maps. Um, and the texture coordinates being on the vertices give us a mapping back and forth between the texture space, which is its own two-dimensional space, and the world space, which is like where the objects exist. And once we're in world space, it means we can move these textures and objects into different spaces. Like we go into view space, we go into like, you know, the model view projection and things like that. And so these texture coordinates are stored as vertex attributes. We've seen this before, right? So I'm just covering what we've seen before on textures. And the sampling is us using our fragment shader to say, where exactly am I between any particular vertices on a triangle? If I'm in a particular position between vertices, I will be mapped to a certain texel. I can sample that texel for color, or I can do what we were doing is I can sample linearly between multiple texels to get a smooth color, because I'm never really going to be in the dead center of one particular texel. I mean, you could be if you're lucky, if you've done things in, you know, in a particularly good way and got your, say, mip mapping perfect so that you have exactly at the distance you're looking, exactly a kind of a one-to-one between fragment and texels. But it's unlikely that's going to happen, so you're probably going to be doing some interesting kind of sampling. The outcome of this is going to be getting a high detail of color. That's what we're looking for. So the surface, which otherwise would have been just color at the vertices and done this kind of interpolation across a triangle, instead of that, we don't have that interpolation, don't have that kind of artificially smooth gradient, which you will see whenever people are showing sort of a simple model for something. I've actually got an example later. I'll show you later. That you can just do simple shading across it, and then it gives you these really hard edges between triangles and stuff. But if you use textures, you can kind of have the texture go over the boundary between triangles so that the boundary between triangles is not as obvious. And also you can include features in something that didn't exist otherwise. So like those cobblestones I was looking at before, even if I wasn't talking about how those cobblestones were playing around with how they were sticking out of the surface or anything like that, even if they weren't playing around with that and giving us the illusion of height, if I was to look straight down from above, I would still see a color pattern that represented cobblestones and grouting in between them and stuff like that. And so I would still have a reasonable belief of what that pavement was made out of, even without any of the kind of pseudo 3D elements that I was showing there. Even just a texture, you can get a lot of information out of it. We can go back and look at the old games again. So there's a particular period I always like to look at, which is between sort of 1996, which is Quake, and about 2002, 2003, which is we're getting into like sort of the mid Halos era, and before we get to games like Crisis and things like that. So that particular era is where us as it's nearly like as technical graphics historians can look through there, and you see things that have techniques, and it's really obvious to see they have techniques and they don't have other techniques yet. So if you go down into the strata of the age of computer games, you can kind of see that Quake has textures, but it doesn't have the other things that I'm talking about. It doesn't even have Phong lighting. You know, so Quake 1 doesn't have Phong lighting, but Quake 2 has Phong lighting, right? So it's really interesting. You can go from one to the next and go, okay, what changed? What's the difference? What can we see that that took it from one piece of technology to the next? Can we see the obvious differences as we go through? So that's why I find it really interesting to look at some of those things. And then every now and then, like I did this week, is I'll just look at some really, really new games, because Genshin is about a year old, so there's not that much, like there haven't been breakthroughs in technology that have necessarily happened during Genshin's lifespan, but Genshin's very specific as well. It has its own lighting model. It is not doing a Blinfong. It's doing a cell shaded lighting model with the idea of two-tone lighting. So there's the color of the object, and then there's the lit color of the object, and those are like the only colors. So it's really a simulation of an anime style shading, which is quite funny because that style came about because of a lack of time and resources. And now it's really funny because things that originally were done to save time and resources are now stylistic and they're an art form, and we latch onto them. So it's kind of interesting how that happens. All right. So what's the difference between a map and a texture? Not much. A map is some information about the surface of an object. Maps are usually two-dimensional data buffers. So a texture is just a two-dimensional data buffer that happens to store color information. They don't have to store color information, so that's one of the things that makes a map more general than a texture. So the texture is a specific form of a map that stores color data, whereas we're going to look at maps that store things other than color data. Again, maps, just like textures, are going to be mapped to vertices via the coordinates stored in the vertices. So the texture coordinate's not going away. And we're actually often still even going to call it a texture coordinate while we're using it for things that aren't textures, because we've just sort of in that language, and historically in that language as well, that the texture coordinate was the thing that was made first, and then we map that onto other maps. So today we're going to look at specular maps and normal maps, which are the normal map and the specular map were both in use on those cobblestones as well. I think, as far as I can tell, those cobblestones were one step further than what we've got today, and they started looking at parallax mapping, but we're not really going to cover that today. You can look it up though. There's a section on Learn OpenGL. So the texture is one particular kind of map, and it's one that we usually call a diffuse map, which is the color of the object, I guess. You can kind of think of it that way, but I mean, you want to be really specific. It is what colors of light are reflected from the object in every direction. So diffuse light is when the light hits the object, and then when it hits the object, it scatters in every direction. So the idea that an object is a color, like it has that sort of intrinsic color property, is its ability to reflect it in all directions, and you can see it clearly. As opposed to specular lighting, which is a direction that bounces, a reflection that bounces straight off an object. So today, we're going to go from the basics, which is the diffuse map. And the diffuse map we've seen already, right? We've been playing around with the diffuse maps. But what we're going to do is add two other maps, a specular map and a normal map, and get a decent look at how they work. The normal map is not complete. I'm not necessarily going to go through all of the maths to how to make the normal map. I'm going to explain it at least. And then we're going to do that kind of thing that we often do with graphics where we say, okay, there is maths. The maths works. If we want to, we can prove that the maths works. But in general, when we're working with something like this, we're going to do a limited amount of that maths by hand. In the same way that, like, you know, when we understand the maths of, say, I don't know, like graph traversals, like graphs of nodes and things like that, if you've done that in other subjects in computing, you don't have to prove the theory of the maths again and again and again. And once you know how to do it, you would use the same kind of traversal. So it's a similar kind of thing where we're going to get enough understanding to rely on something, but not necessarily get the full expertise on how to create those mathematical algorithms. Okay. Did I? Oh, no, right. always thinking that I've talked about a slide before I got to it. So 3 maps that we're going to be using, and this is something that is reasonably standard nowadays, depending on the system that you're using, but it's reasonably standard now to have a diffuse map, a specular map, and a normal map on pretty much every object that we have. What these are going to do is give us slightly different capabilities each. So the diffuse map is one that we're used to. It's the texture, it's just colors. The specular map is a measure of the shininess of the surface. So the cool thing about the specular map is we can actually divide the surface up now between those bits that reflect light directly and those bits that don't reflect light directly. I've got an example later, which is actually the one from Learn OpenGL, which is a perfect kind of example. It's one that's been used a lot in graphics over the years, is like a barrel with metal on it. So old school pirate ship kind of barrel. It's a wooden barrel with bands of metal wrapped around it to hold it together. This one's a one to make it easier, so it's just a cube crate that has metal along the edges. And so what we can do is we can say that parts of this surface should be shiny because they're made of metal. Other parts of this surface should not be as shiny because they're made of wood. If we were to try to do this without something like specular maps, we'd end up in a situation where we'd have to combine two models together. And then we'd have a whole lot of extra verts, maybe, that we didn't need. Get it? Extra verts. I've been... It's not as bad as when I said we're going to do lighting perverts. I was like, no, should not have said that. I shouldn't have said that again. But anyway, what we can do is we can have the idea of multiple different surfaces on one object without having to make multiple objects to make it work. So it's a pretty cool thing. It helps us a lot like that. Normal maps give us what I'm calling surface features, the illusion of three-dimensional information. So the illusion of geometry on a surface using these normal maps. I'll talk about that more later because it's a nice little setup, but it's fiddly to make it work. So each of these maps is storing their own information, but each of them is like storing the information just exactly the same way that our textures are. It's just data in texels, but they're not all texels. We even looked at like doing light maps, which was not really mapped to objects in the same way that these are. They weren't kind of intrinsic to these objects, but they had lumals. So each one of these has its own kind of, I don't want to say pixel, its own unit of data that holds information inside it. I actually don't know the names of the unit of data inside each of these. Specules? Normals? I don't know. I'm not going to try to make them up. So what we can do is then, depending on what we're doing in our fragment shader, we'll sample from these different maps in different ways. So I'm going to talk about those techniques as well. These can all be sampled using... Hi, Nicole. These can all be sampled using the same... Hello, Michael, as well. And Jason. A few people said hi earlier. These can all be sampled using exactly the same kind of techniques we use with textures. We're going to use the texture coordinates to sample into the maps. And if you remember, our texture coordinates are pretty simple. They're between 0 and 1, they're a floating point number. The beauty of having them between 0 and 1 and a floating point number like that is that these maps don't actually have to be the same resolution as each other. They don't have to be really specific. We can slap different maps on the same object that are actually different sizes, but because the UVs, the texture coordinates, are mapped from 0 to 1, they can find any position that they need to be on any of these maps without them being exactly the same size. So that's kind of cool. And we're not really limited yet to just these. For any kind of map that we want to add to our objects, there's a thing called parallax mapping as well. Although I don't think parallax maps are actually a different map. I think they're just using normal maps to do this. But I have to look that up to figure it out. But we now have a situation where instead of just going, okay, the material is the texture, now we could have a material that has multiple maps in it. So it has a color map, which is it has a diffuse map, which is the color, sorry, specular maps, and normal maps. And we can say, depending on which part of the lighting algorithm we're using, we're going to sample from a different map. I think I may have already talked about this slide, a justification of why we'd use maps. This is all, I guess it's still worth talking about. This is all kind of part of one of the measures under which we decide how efficient a scene is going to be to render. And it's interesting because one of the ways that we decide how efficient a scene is how many triangles there are in the scene. Like you will see a lot of artists when they're talking about 3D models, when they're talking about scenes and worlds they've built and stuff, will be talking about things like the number of triangles, number of polys, number of tries, and it's super important because the more triangles you have equates roughly to the amount of processing time it takes to render this thing. So when we're working in film, we can have millions of tries because we know we've got minutes to render a scene, to render a frame. Whereas when we're working in real time, we have a frame rate, which is the number of frames we want to deliver per second. And the frame rate can fluctuate quite a lot depending on different things that are happening. But one of the big factors is how many triangles do we have to process. So if we're trying to make the number of triangles efficient, we're trying to reduce the number of triangles we use in a scene, one of the things we can do is say, okay, let's have a very low poly count in our scene, but we still want certain amounts of visual fidelity. And if we want that visual fidelity, then maybe we need to have really good surface detail on those triangles. And that's where all these techniques actually originally came from. The idea that we couldn't have enough triangles to model things in great detail. So you remember that that miniature that I showed you that had like, I think it was 130,000 tries on it for a little 4 centimeter miniature? That was excessive. But because it had so many triangles, it didn't need any of these techniques. Like it just had a texture wrapped around it based on the photos that were taken. And we got a good amount of surface detail. We'd have a good amount of like we'd be able to see every little bump in it and stuff like that. But if we were to put that into a scene as just sort of a static object on a shelf and all the other objects were at that same level of detail, we would end up pretty quickly using up all of our rendering time just processing all of those triangles. So what we want to do is have low poly count geometry that still represents the same level of detail. And so the thing we're going to do for that is to put all the detail into the maps and have us just sample the maps, because sampling from the maps is pretty quick. That's just reading a bit of memory, rather than having to process multiple surfaces facing in multiple directions, and sort of you'd end up spending a lot of time in your vert shader doing that because there's all these extra verts. Extra verts. Hate them. Talk too much. I'm kidding. So this is a justification we used for using textures instead of adding a whole lot of vertices to surfaces, and we can do this just as much for the reflectivity of a surface or the extra geometry we wanted to show in a surface than we can for the color. So the same justification works. So let's look at diffuse maps. This is going to be quick because I don't need to teach you how to work with diffuse maps because I already have. So I say here diffuse maps textures, right? It's something that we already know about, and all we're doing now is renaming the concept of textures because we now have a better understanding that textures are just one type of map, and now we're going to be using more maps. So we already know how this works. I don't really need to tell you too much about it, other than the idea that now if we're going to add other maps for other purposes, we're going to reduce the work that the diffuse map, the texture, does. So the diffuse map, which is the color of the object, is only going to be involved in the ambient and diffuse steps of the lighting. So we're only going to use these colors when we're talking about ambient light on an object or diffuse light on an object. But now we're taking specular out because we're going to replace the color that reflects specular with something else in a moment. So I don't really have to say much about this, but this is the example from LearnOpenGL I was talking about. It's a wooden crate with a metal frame holding it together. So I'll show you pictures in a second because we've got a cube rendered on LearnOpenGL about this as well. So we don't we don't really need to go back over this too much, but you know, it's what I've just been saying. We map the textures um uh the vertices and the fragments. We map the texels to the world coordinates. But where we're thinking about this differently now is how the Phong lighting equation deals with it. And as I said a second ago, we're only going to be using the ambient diffuse there. So we're going to pick up the color of the surface, which was KA or KD in the algorithm. I've actually got it written out later, so we'll show it in a second. And we're going to use this for the ambient and diffuse, but the specular we're going to use a different map for, which I'll show you in a second. And this is the specular map. So the specular map is the new thing that we're looking at today, and it is a map of shininess. I just remember somewhere else I called it a map of reflectivity, but it's not actually really reflective. It's just shiny, which is a subtle difference in that reflectiveness we'd expect to see an image or something else like a mirror or something, and we're not doing that yet. We're going to do that next week. But this is a map that says which part of this object is shiny, in a sense. So for this object here, the suggestion that we're going to make with this object is that the metal around the edges is shiny, but the wood is not. So we're making an assumption that the wood has aged to a certain point. The whatever paint or lacquer that had been on the wood is no longer shiny, but the metal frame around the outside edges is shiny. And that kind of makes sense because the way this is painted, the wood has split, and it's very worn, so probably not as shiny as it could be. But if you're going to get really kind of specific and realistic about this, some of this wood might be shiny. But in order to have our effect really, really sell itself here, what we've got is a specular map that is saying these bits here have a lot of shininess on them, and this square in the middle that's the wood has no shininess whatsoever. That's going to make it really obvious when we're rendering this, the difference between the shiny and the not shiny. So the specular map is often a grayscale map. So it's often working on the theory that when something has specular reflectivity, i.e. it's reflecting directly the light that hits it, the assumption a lot of the time is it's not changing the color of the light when it reflects it. So that kind of makes sense because most objects that are shiny are just going to bounce back all of the light that hits them, and it will look good to us if we start using colored lights, because you'll get to see that, you know, the diffuse part of the object retains some of its color, whereas the specular part of the object really takes on the color of the light that hits it. So the trick here is that these sections that are white, in a sense, are going to reflect all the light that hits them. The gray sections are going to reflect part of the light that hits them. And the black sections are going to reflect none of the light that hits it. So we're going to rely on those sections of the diffuse part to say this thing is this color, but there's no direct reflections. So the specular map is not actually a color map as such. It's nearly like a quantity of reflection map. If we really wanted to, we could do this as a single floating point number. And this, because the RGB values in all of these are the same as each other. But sometimes you do want to tint the reflection. So if I wanted the banding around the outside of this crate, I mean, like, it's probably not a crate in that case, to be something like gold, then it would have more red and green than it would have blue. It would reflect more yellow light than other lights. So we can have it like that. David's asking, why don't we use transparent pixels for specular maps? So we're not necessarily thinking about this as something that's transparent or not. We're thinking of the quantity of the light reflection here. So whether it's transparent or not kind of makes no particular difference to this, because this is, are we reflecting light or are we not reflecting light? So it's the quantity of the red, green, and blue light that we're reflecting. If we were to add an alpha to the specular map, it wouldn't really mean anything because there's no such thing as transparent light. Because what we're doing is we're saying the light hits us, and this is the quantity of the light that comes back off in that direct reflection. And the alpha has no kind of bearing on that. In a sense, you can think of these RGB values as being the alpha. So here, the RGB values are 0, which means the specular doesn't do anything, but the light still hits the object. The specular map is not like laid on top of the texture, stopping the light from hitting the object. This black here is just saying that we're not going to specifically reflect specular lighting. So instead, what we're going to do is let the diffuse lighting take over there. The way that this actually works is, what was I going to say? I think, is it the maps here? Oh, no, okay, I guess what I'm talking about on this slide. We're going to sample from the specular map in the same way, using the texture coordinates, which means we're going to be here, and we're going to be saying, okay, in these areas, we're going to get a 0 from the specular map. In these areas, we're going to get a non-zero number. What we do is we calculate the specular component of our lighting, and the KS, which is like the specular reflectivity of the object, is whatever value we sample from here. So here, if the KS is 0, what we're going to get is that there will be no specular light reflected from the object. And here, if the KS is a non-zero number or a positive number, well, it's only going to be between 0 and 1, then that's how much light gets reflected off the object. So the trick is that if we wanted to, we could have made this whole thing white and this whole thing black and said this bit is reflective and this bit is not reflective, you know? So the cool thing about this is they've put some detail in here, so there's scratches and textures and stuff like that, so we can show something that's like a beaten old metal object where there are some parts that are more reflective than others. So you got like the places where it's worn and scratched more are more reflective because it's more bare metal, and the places that are darker where rust is covering it up a bit, so it's not as reflective. So you can get some really, really cool stuff going with partially reflective specular maps. So here are some images of the difference between the two, where if we were only using the diffuse map and we were using our old lighting equation, which was going to do specular across the entire surface, i.e. none of the specular reflection here has been multiplied by this. So the maximum this thing can do is multiply the specular by 1. But what it's doing more importantly is a lot of the time it's multiplying the specular by 0. So this is actually taking away specular reflection. And then what we can do is we can have this cool kind of scene here where here everything was specular. So the entire surface of the crate looks like it's shiny. It's nearly like we've got a crate here, we've wrapped it in cling wrap and it's reflecting light. So it's a little bit unrealistic there. But with the specular map says, okay, any fragments that existed inside this square will get 0 specular reflection. So we will multiply the specular component of the lighting that we've calculated, which you can see is definitely greater than 0. There's specular reflections happening right here, but the specular map says, no, hold them back. We don't want this bit to be reflecting light. We want this bit here to be reflecting light. And it makes it look really cool like that, because as you walk around it, you will see only the metallic parts of it reflecting light, and you will read them as metal. Like here, when we see this, we don't read these as different materials as easily. But if we see this, we go, ooh, it's a metal frame on a wooden box, you know? So it's all about getting us to start believing the properties of the surface of this object, even if they don't actually exist. So it's kind of nice, right? This one with the specular all at 1.0, and it's only all at 1.0 because there was no specular. And here, the specular is being modified per fragment to values between 0 and 1 around the edges, and a flat 0 here saying no specular. So that way we get this cool kind of look. The cobblestones I showed at the beginning had a bit of that as well, where on the top surface where people have been walking on it and polishing and rubbing it, they had specular reflections, but in the gap where it would be like rough, probably mortar, I think, in between the cobblestones, or even just dirt in between the cobblestones, wouldn't reflect light. So they did have a specular map on that. I would love to be able to pull that apart and find those maps. But I'm not sure if you can do that without reverse engineering the game, or if they've published anything. But I don't think Genshin publishes their technical side very much. Even though they've got an interesting technical side, I think the there are a lot of games where it's quite deceptive, where there's a whole lot of work that have gone into them, and a great deal of that work has gone into them to make them look like they're simple. And I think that's really interesting. There's heaps of games that are made to look like they're really particularly kind of, I won't say low quality, because it's not quality that we're thinking about here, but low technical complexity. So they're made to us to bring us out of the idea that this is a high-tech computer game and to bring us into this other feeling. And often it takes more technology to bring it back in that direction. Sam's saying lo-fi. Yeah, totally. Like the whole idea of lo-fi is like we've got this really wide frequency spectrum of audio that we can deliver via, you know, MP3s or audio files or whatever, anything like that, or streaming and stuff like that. But what happens if we really narrow the band of what we can do? And it's really interesting because all the lo-fi stuff actually, because it doesn't have all the possible frequencies of the audio spectrum, it does actually chill us out, because it's like, don't worry, there's not that much information. You don't have to think about all these kind of sounds coming in. You can just have this really kind of predictable band of information. So, and a lot of that is about really carefully choosing which frequencies you're going to deliver to someone to make them comfortable. It's a lot of interesting sort of artistry behind that. Anyway, I did say we were going to talk about the algorithm. It's not really that difficult, because this is a standard Blinfong right here. So the total illumination, I guess I could have just put a T here, but the total illumination is the ambient light multiplied by the ambient color of a fragment, and then the diffuse light multiplied by the diffuse color of the fragment multiplied by the direction of the light, dot product with the surface normal. So we've done that before, right? So that's like, if it's dead on, it's brighter. If it's on an angle, it's less bright. And then here, first time we've actually written this out, actually, is the Blinfong algorithm, but it's not super different from the other algorithms. The calculated halfway vector dot product with the surface normal to the Phong exponent, and then the bits that we're used to, which is the specular reflectivity of the surface versus the specular light that's hitting it. So the ambient intensity light's going to be its own thing, but the color of the light, the intensity of the diffuse light, and the intensity of the specular light are probably going to be the same, because the light does not really determine, the type of light doesn't really determine specularity. The type of object usually does. So what we're going to get here is the ambient and the diffuse are probably going to come from the diffuse map. If you really want to, you can have a separate ambient map to diffuse map, but because diffuse and ambient light are thought of as basically being the same thing, just with more bounces, in a sense, we would usually use the same map for both of these. So Ka and Kd are just sampling from the diffuse map. This shouldn't be new to us. It's how we've been working with textures. But now what we have is the specularity of the surface no longer uses the diffuse map, it uses the specular map instead. So what we're doing is we're saying we're separating these things. The diffuse reflectivity of the object is no longer connected to the specular reflectivity of the object. We need to use them in separate ways. That way we can do cool things by saying, okay, part of this object is simply not reflective, other parts of this object are. And so the specular map gives us control over that. So a little bit of information about how we might even create these maps. I will say the second point, we're not always going to be making these maps ourselves. I go back and forth when we're talking about graphics. I go back and forth between talking about what you would do if you had a team of people working on something and you are the graphics programmer. And it's usually not just graphics. If you're going to be a programmer on you know, any kind of real-time immersive or non-real-time immersive stuff, you're not just going to be a purely graphics programmer. So it might be support of the art pipeline, or it might be gameplay programming. It might be doing things like testing and stuff like that as well. But if you were at a point where you were purely a graphics programmer, you would probably not be creating specular maps. You'll be relying on artists to do that. Um, but I thought I'd talk about it anyway because it's not that hard to do. So going from this to this is actually quite easy. So all that's happened is someone has taken this image, put it into even something as simple as like Microsoft Paint. I could do this in Paint. Just joking because I do everything in Paint. And what we've done is we've taken the center square here and we've colored it black. So we've just changed its color to black, and we've taken this outer rim here and we've desaturated it. So we've taken all of the colors out of it and we've made it purely black and white. And we can fiddle around with the contrast here. We can fiddle around with the brightness of this thing to change how specular something is. But all that was just a conversion of one image to another. And you can do that kind of thing if you want to. If you want to test this out, you can make your own specular maps that are wildly kind of obvious that some parts are reflective and other parts aren't, and see how your lights work with it. So I could take a black square in Microsoft Paint and a white brush and just do these big stripes of white across it, and then run that through my my lighting algorithm and then check whether my specular lighting is using the map properly or not. So yeah, what we would generally have is the artist would decide which parts of the model are reflective and which parts aren't. So if they've made something and they've been really specific to say, okay, so this is, I don't know, some kind of fantasy knight wearing armor. And so here are these sections that are literally plates of metal on a person, and here are the gaps in between that are like, I don't know, leather buckles or chainmail underneath, which is not quite as reflective. They would make their own specular map going, okay, the big plates are very shiny, but even on those big plates, in the crevices, they're less shiny where dirt has accumulated and stuff like that. The chainmail is very specifically shiny, so it'll be like little spots of light, and the leather straps and things holding the whole thing together are going to be very not shiny, so they're going to be completely black in the specular map. So your artists can put that kind of thing together quite easily. I said before that our maps don't have to be the same resolution, which is nice. The thing that they will be, however, is that we're going to be using single texture coordinates. So the beauty of having these maps, kind of thinking about them being placed on top of each other in a sense, because they're not on top of each other, because they're different for different purposes, but you can think of them being sort of superimposed on the same position on an object. The beauty of that is we have a single set of texture coordinates, and from that set of texture coordinates we can then access any of the maps. So it means that we're not overburdening our vertices with extra data in order to use these maps. All we're doing is saying, look, you've got a way of mapping into 2D space, into a sampler. So sampling into a two-dimensional data buffer via your texture coordinates. So we're just going to keep those texture coordinates, but we're going to add multiple extra buffers to be able to get different kinds of data out of them. All right. Going into break time, we're a bit early today. I actually think, like, having written this lecture, I was finishing it last night. I actually don't think we're going to go for a full 2 hours today, but we'll see how we go. I mean, because I know that the content, if I really wanted to, I could rush through this content in an hour and a half. It actually gives me more time to elaborate on things and stuff. So we're breaking a little earlier than normal. We probably finish a little earlier than normal, but I don't know. Whenever I give students an early mark, they don't usually complain. So here's some homework. It's not really homework, but I find this really interesting. And this week, all of my examples came from me doing this kind of homework. I did it by accident, and you will find this happening by accident more often than it may have happened in the past, but you can do it intentionally as well. So choose a game or a film. If it's going to be a film, don't necessarily just look at something that's purely filmed. You probably want to have something with CG and VFX in it if you're doing this as a graphics analysis, and pull it to pieces. So look through and see if you can figure out what's happening. So see if you can say, oh, I see this technique. One of the most obvious ones that you can look at is you can see specular maps in action. It's really obvious when a specular map is happening. So I showed you Warframe. Was it last week or last lecture? No, it was last week. Last lecture I was showing the division. So Warframe really obviously has partial specular maps on all its metallic objects, and it does that to make sure that they don't look perfectly smooth. They look like they've got chips taken out of them and stuff, and they have sections that are reflective and sections like in crevices that don't reflect the light. So the way the Warframe looks, I just love describing this way. The way that Warframe looks is real edgy, but not the kind of edgy. It's not like personality edgy. He's a little bit as well. The main character's a little bit edgy. But you can see the edge reflections on all the surfaces because the specular maps look a bit like this, where there's this kind of like stronger white line on the inside edge here. We'd probably want one on the outside edge as well, but maybe you can't see it that well because this is on a white background. But you can definitely see it on the inside edge here, that it's brighter, it's whiter than any of the other parts of the specular map, which means that anytime that specular reflections happen, this edge looks like it's catching the light and reflecting more, which is a good thing for an artist to do because metallic edges of objects tend to catch more light because they're actually a curve over the object. You know, it can be so small a curve that we're never going to model it. You know, we're going to model this thing as a perfectly straight corner, but in nature, in the real world, perfectly straight corners don't tend to exist. Instead, every corner has a certain amount of rounding on it, and if that's on a crate that's been bouncing around and it's rounded, you should see more reflection of light on that edge. So here we can definitely see that whoever made the specular map is taking that into account and trying to make the inside edge a little bit shinier. So, specular is one thing we can see, but there's also things you can be like, I don't know how they did that. And I think that that is one of the things that gets you into learning about these things, is you build up a curiosity for things because you look at them and you say, I don't know how they did that. So, for example, you could have been in the same situation as me in Genshin and, like, you know, just tilted your camera up and down and looking at those cobblestones and going, the cobblestones appear to disappear at some point in time. Not only do they appear to disappear, they look like they're sticking up out of the ground, yet they do not obscure anything that looks like it should be behind it. Like, what's going on here? You would end up, if you could find your way through the investigation enough to find out, you'd end up at normal mapping and parallax mapping there, I think. But yeah, so when you're looking at it, look at the lighting and shadows, look at what happens when you move around. You'll be able to tell the difference between whether something has been light mapped or something has been has calculated ambient lighting. Especially if something has calculated ambient occlusion and things like that. You'll be able to see whether if you have games that have you carrying a light source and stuff, like how does that affect the scene? Are these things dynamic or not? It's really, really interesting. And then you will find some of these will do really interesting things where it's like, is this art or processing? You know? Because you'll see some games that are very, very careful and they worked very, very hard with their textures to make things look interesting without needing processing to make them look interesting. So particularly look for games that are hyper stylized, not realistic games, maybe games that don't even have a realistic lighting model, but they do something else instead. And did they manage to strike a nice compromise there where something looks interesting without having good lighting? And then also, can you see where people have cut corners? Like, there's always tricks used to conserve processing time. So you'll see that, like, characters, things that occupy a significant amount of screen time, might be very highly detailed. You might not be able to see the polygons in them because they're so detailed. And then you go, like in the Division, where I said, oh, look at this block, this concrete block. It's like, this thing is just a cube, right? This thing has so few triangles on it, you know. And you'll see how they can save processing time by making environments that are off in the background really low detail. Like a building in the background is just one big rectangle with a texture on it, and so there's no geometric detail in the windows or anything like that. It's just a texture. And another building which you're intending to go into, that's something you're supposed to see up close, suddenly has all this extra modeling detail, and it has little bits of rubbish around the bottom, or it has trees nearby and all this kind of stuff. But the ones in the distance, they don't bother with those. It's old school techniques, right? This is like matte painting in cinema and stuff like that. Okay, so I encourage you to do this. You're probably going to do it by accident after taking this course. You can see, I see how this stuff is working. But it's really interesting to see which bits can you identify, which bits weren't you able to identify. Are there things you want to look up? Because I think the best thing for learning is curiosity. It's probably more important than anything I'm just kind of like trying to push into you. Is like, if you're curious about things, you'll probably learn more about them. Okay, so let's go on break now. It is 11:01 by my clock here. Come back in 5 minutes at 11:06, and we'll continue, and we'll start looking at normal mapping. Hello. I'm back a little early because someone came in to say hi, so I'm just wondering if she's gonna come and say hi. Hello? Hello? Yes? I don't think she actually wants to say hi. She's just meowing at me to try to convince me to leave my seat. Because basically, like, she thinks I'm boring when I'm sitting here. She wants me to go play with her somewhere else, so she'll just meow at me until I follow her somewhere else to go give her a pat. But she doesn't want to actually hang out when I'm sitting here at my desk because I think that me sitting at my desk signifies to Chicken that I'm going to be boring for an extended period of time. But hello, here she is, being manhandled. Okay, so back to the lecture. Well, she actually does look like she's going to sit here now. We're going to move on to another kind of map, which is similar to the others, but with some subtle differences. And these are these things called normal maps. So normal maps, as opposed to abnormal maps. I'm kidding. It's a joke. It's a joke. It's just about normals. It's a weird word to use. So we've gotten to this point, right, where we were able to interpolate colors across a surface by mapping them to a texture, right? So we're mapping our texture coordinates at our vertices, and so we can interpolate colors. And we say, all right, let's go one better than colors. Let's split up our surface detail between diffuse colors and specular colors, because the specular map is colored. You can actually put colors in it if you want to. You can do some really cool stuff with that if you want something to look like iridescent. Like if you're doing like a model of a beetle or something that reflects different colors depending on the direction of the light that hits it. That's a cool shader, actually. You could do something really cool with that to say that, like, depending on the angle of the light, like direct light is direct light is, I think, bluer, and then like if you go at different angles it goes green and yellow and stuff like that. That'd be really fun. But anyway, we're not talking about that right now. But yes, we have done things with colors and reflectivity of the surface. And so the question is, if we want more interesting data to sample, so to put into a map and sample, what else do we use to calculate lighting? And one of the things we use is surface normals. So it's like, okay, up until now, our surface normals have had two options. One is we just raw calculate it. So we calculate it based on the triangle. And calculating based on the triangle is going to make each triangle really distinct and flat. Or we calculated them based on the verts. So we get, let me just, so there's two ways to do this. I'm going to draw two surfaces. So here's this surface and a very similar surface like this. And if I calculate the normals per triangle, my normals look a bit like this per fragment. So this gets us your really, really obvious, like, these are hard edges. The lighting in these corners here will change starkly from one to the next. If instead we have normals specified per vertice, and then the normals that we generate when we're doing our lighting is an interpolation of these normals, what we're going to get, I apologize, they're a little bit bent. We're going to get this smooth gradation of normals, and these corners are going to disappear because the linear interpolation of the normals is going to have the normals just kind of transitioning smoothly across the surface, and you will not see those corners. So it depends whether you want the corners to appear in your lighting or you want the corners to not appear in your lighting, is you choose between those two. However, what if there's a third choice? What if there's a better choice where instead of just interpolating these normals and saying we have only two choices, one is we show off all of our verts and our edges, or the other is we totally smooth over the entire surface. So what if we want surface detail that is not in our geometry, and that's where we can use surface normals. So if we're going to interpolate different colors across the surface, we can get all kinds of colors where there are no verts and there's no geometry to support this, but we've got colors so we can make it work. So if we're going to do this with normals, how would we do this, right? We're going to store these in a map, which we're now calling the normal map. And we think about what have we stored in these maps up till now. So the diffuse map and the specular map are both storing RGB colors. So they're just storing 3 float vector colors. So what's a normal? Normal's also a 3 float vector. I mean, we can put a fourth coordinate on it, and a lot of the time we are going to put a fourth coordinate on it, but a lot of the time we're doing our calculation, the fourth coordinate's going to get ignored anyway. So, I mean, one way or the other, storing the normal in a map is the same amount of effort as storing the color in the map was before. So we're getting to this point where it's like, oh, this is super convenient, right? This is too easy. All we're doing is just making another texture. I mean, we're not really going to call these textures, right? Only one of them is a texture, but we've got a diffuse map, a specular map, and now a normal map. And in terms of data, they look really similar, because the normal map could be just read as color information if you wanted to, because like any three-dimensional coordinate space, you could look at it as a color if you want to. You can get some really wacky colors out of it, but like it'll work, right? So it's just a 3 float vectors, the same thing. So we don't even have to do anything special with the way that we're storing data in our maps to be able to use a normal map. So what do normal maps do? It's really obvious when we look at a diffuse map or color texture what it does, because it's just like, all right, across this surface, we take these colors and we just put these colors on this surface. But what we're going to do here now is say we're putting these normals on this surface, right? And so we've just got to remember what normals do and how they work for us. And then we get an understanding of why this is going to help us. So the normals can change per fragment. So here, if the normals per surface, so this entire surface has the same normal, we don't see anything strange on our surface. It appears completely flat. But if we wave some of these normals around, you know, and these can even cross over each other and stuff like that, we can wave some of these normals around, what we're going to get is each fragment is going to appear to be aiming in a different direction from the other fragments around it. So what we can get is some parts of the surface aim towards the light, whereas other parts of the surface aim away from the light. It's going to change the way the lighting equation works. So some of the normals are going to make part of the surface look bright, and other normals are going to make part of the surface look dark. Some of the surface is going to reflect better than other parts of the surface, because the normals are going to make the specular light aim directly at the camera, whereas in other places it's not. So you can get this kind of doubling down on what the specular map was doing. So the specular map was just turning on and off reflectivity. The normal map now is going to give us the opportunity to aim certain parts at the camera or away from the camera depending on the angles. So I was getting that when I was looking at the cobblestones earlier, where some of the cobblestones were reflecting light directly into the camera and others weren't, and they didn't appear to be flat. They appeared to be like kind of on an angle. Logan's asked the question, does this mean we can use the normal map to control the roughness of the surface? I would nearly say yes, 100%. That's exactly what it's doing. So if we have a normal map that's really consistent like this, it gives the appearance of a flat surface. If we have a normal map that has a lot of different normals aimed in different directions, it's going to give us the appearance of a contoured surface, a surface that has a lot of little micro kind of bumps and gaps and things like that in it. So here's an example of what this kind of looks like. So if we don't have any normal mapping, and so all the normals are consistently flat off the surface, what we're going to get is a patch of light from our specular that just sort of spreads out and it attenuates nicely using its Phong exponent over time. And the diffuse is very even as well. But if we do normal mapping, what we can do is we can have all of these edges of these bricks here with normals that, instead of just coming straight off the surface, are actually aimed off to the side, in a sense. So they're not coming straight off the surface, they're aiming off to the side, and the ones that are aiming towards this light source are picking up that light and reflecting it. So they're looking like they've got an edge that aims towards the light source, when in reality their geometry has nothing of the sort, right? The geometry is just a flat. This is like a 4-vert rectangle with 2 triangles, right? There's no detail in this at all. But if the normal map is able to send off these normals in lots of different directions depending on the position they're in, they're going to pick up our lighting equation and they're going to change significantly, because both the diffuse and the specular have a significant component depending on where the surface normal is aiming. So if the surface normal is aiming towards the light, the diffuse gets brighter. If the surface normal is close to the halfway, which is a measure of whether the light reflects towards the camera, it's also going to get brighter light. So you can just see immediately the huge difference we're getting in these two images. This is the same image, the same lighting situation. So this has been made to show this off. Exactly the same situation. But here, the normal maps are waving these normals around. So it's not just these nice bright edges that we're getting. We're also getting, in the crevices in between here, we're losing light. Because in the crevices, they're not giving us a nice consistent normal that points forward. There's a bunch of normals here that are probably pointing away from the light source. So these fragments are now getting darker because the light shouldn't be reflecting outwards as nicely. And so we're getting this kind of level of contrast, which is giving us the appearance of surface detail. And particularly these worn and chipped kind of bricks here look really good like this, because every little pit in the brick has sections on one side of it that have the normals aimed in one direction, sections on the other side the normals aimed opposite direction. So some parts are getting darker because of the normal map, and other parts are getting brighter because of the normal map, and it really gives the appearance of three-dimensional information here, whereas there's no three-dimensional information. There's only normals. So it's pretty cool. Oh, a couple of questions. Oh, Jason's tangents and bitangents time. I'm not going to go into super detail about those. I am going to explain a bit of them, but not going to go into super detail. Jason saying normal maps are a subtype of bump maps, right? I think it's the other way around. So bump maps are something that we don't really use anymore, and bump maps were a single dimensional form of the normal maps in a sense. So the bump maps just said, does this thing bump outwards or not? And then you'd have to do some extra calculation to make it work. Whereas the normal maps are about having lots of normals and then using them. I actually, for years, just used them both interchangeably. I called these bump maps, which is incorrect, because bump maps is, I think, a simpler form of technology that has basically been deprecated by normal maps. If I remember correctly, I'd have to go back and kind of redo a bunch of old study on them to be sure of that, but I'm pretty sure that's the case. Hamish, the normal maps do crazy shit. I had no idea that was just lighting. Yeah, so this is amazing that it can do this much with only the addition of a map, and the only thing it's doing is changing directions of normals. So no geometry between these two. A lot of it, you could look at it and go, there must be geometry added to these. Like even with the Genshin example I showed earlier, we were looking at that really closely. We were picking at it, and you could have sworn there was 3D geometry popping out, and there wasn't. There's actually a really good. I'll show it later. I'm jumping ahead. There's really good examples of using normal maps to create optical illusions. And again, it's the same thing as we've always been doing. How do we do simple things that trick the eye into believing other things? So this contrast and brightness between objects makes a huge difference. The first games that did this, that went from this to this, they kind of they shook our worlds, and it was really interesting to see that. Anyway, so the effects of normal maps. You can already see just from that one image the simple effects of a simple normal map. So we can see that this significantly alters our lighting calculations, and even more so for specular. So it does affect diffuse. If you have only diffuse, you can still see the effect of a normal map, but it's not really until you get specular reflections, and you see the specular reflections popping off the corners of things. And when I say corners, I mean corners that don't exist. There's no geometry for those corners, but corners of these bricks. When you see them reflecting light, then you know that it works. I mean, the downside of this is that these bricks probably wouldn't have any specular component in the real world, but having them with a bit of specular here allows us to really see what's going on. So the key thing here is we can define shapes without there being any geometry. Actually, I'm gonna go to, because I think it's a Wikipedia. Normal mapping. I'm just sort of jumping around here a little bit. This image, is there a larger size? There isn't. Oh, there you go. This image is really cool, because what they did was they rendered the geometry on the left-hand side. And then what they did was on the right-hand side, they calculated all the normals from the left-hand side, and then they just made the normal map on the right-hand side based on where the normals would be in the 3D image if you viewed it from top down. So this right-hand side has zero geometry. Absolutely zero geometry, only normals. And then if you have this kind of stark lighting like this, with these normals, you get this response. I mean, you can see they've actually made it worse for themselves by doing proper shadows. So they're doing I don't know whether this is ray tracing or just like basic shadow mapping, but the cast shadows tell you more about the left side, but the right side is actually giving us a decent believability of three-dimensional objects without actually creating geometry for them. And the beauty of this is, you can see this and you know that it's not real, but you know that also if you were to see this and it's hidden under other layers of lighting and stuff like that, you're going to believe this. You're going to be happy about this, right? So I think this is a really good example of something that's really overtly showing you that it is not real, but you still like look at it and go, I could believe some of that, you know? So I think that's really cool. Anyway, we'll leave that there. Maybe we'll come back to it in a second. Yeah, so the key in the normal maps is the definition of shapes where there is no geometry. So let's look at how these are actually encoded. So if we want to, as I said before, if we want to, a three-dimensional vector is 3 floats. So if they're 3 floats and these are normals, so their floats are going to be between 0 and 1 because they're normalized, we could view this as RGB data. So we need to kind of wrap our head around this to view it as color data, because normals are not colors, right? So it's going to look a little bit weird to us, but it's not super weird because we can still recognize what it is based on these normals. So the reason why this thing is mostly blue, it's not entirely blue, it's like it's kind of a purpley kind of color, but there is kind of more blue component than anything else in it, because if we read vectors as colors, 001, which is the z-axis pointing straight towards us out of the front of this map, will be mostly blue, which is why the majority of these, especially in the flat surfaces, are a bluish color. It's not exact, it's not perfect, because like not many of these normals are like pointing straight out at Z, but the average normal, which is the same as what the default surface normal would have been in this perspective. Like the default surface normal is coming perpendicular to the surface, would be a 0, 0, 1 along the z-axis. The other thing that you can see, which is interesting here, is you can see the color changing as the normals point further away from the straight along the z-axis. So if we take our RGB, so R is X, so red is going to the right, green is Y, so green is going up, and blue is Z, blue is coming out towards us. So you can see the top edges of all of these bricks, which are where the normals are not pointing straight towards us. The normals are tipped upwards, so we can get this lighting coming off the top edges of the bricks. They go green. On the right-hand side of the bricks are going... They're actually going a kind of a magenta. That's actually a cyan. It's a mixing of the green and the blue. But they're going more green. And on the right-hand side, they're going more red. So as we tip and we get more along the other axes, we're going to see more of that color. So a lot of the time when we're looking at normal maps, we'll look at them in color because we can see whether they're sort of working or not in that regard. But this representation is something you'll just see every now and then. Artists might use this when they're working on it, but it is in a sense a misrepresentation of it, because this is meant to be directions, not colors. But it's very, very hard for us to see directions. Like there's nothing visual about them. So if we map it to colors like this, it's not too hard. And we can see like the top right corners are nearly white, the bottom left corners are nearly black, because that's the difference between like extra quantity in all three axes gives us like a sort of a 45-degree angle off the surface, and in the other direction lowering the intensity of all the vector is aiming it back down the other angle. So you can kind of see just by looking at it that you can have a reasonable idea looking at this that you can understand where these normals are aiming. Haha. Hamish, you ask a good question. Can artists convert a 3D model to a flat model plus a normal map? Yes, they can. I have a slide about that later. I will show you that later. But the answer is yes, and I will show you how it works. So, how do we use a normal map? The intuition is, it's the same as diffuse and specular maps, right? So all we do is we say we sample the normal. We can do this, right? We're just using our texture coordinates into the normal map. It's exactly the same. We just said we're storing normal data, and we just replace the n and we calculate. Probably should have had this on a different slide so that I could get it easily. But yeah, all we're doing is replacing these surface normals, right? So we have a map of normals, we replace the surface normals, and we just throw it into our lighting equation. Because we've got our map of normals here. And then we throw them in our lighting equation. It should just work, right? Right? It's a classic thing. When I ask you a question like that, it means the answer is no. So I've got a really simple example here. So I've got a really simple triangle here going from 1, 0, 0, 0, 0, 1, 1, 0, 1. So it is on the XZ plane. It's like flat ground. Its default normal is the y-axis. So its default normal would be pointing straight upwards if we weren't using any kind of normal maps or anything like that. So its default surface normal would be 0, 1, 0. If the average normal in the normal map, so this blue normal pointing out straight to us, straight towards us is 0, 0, 1, it's pointing along the z-axis. So this makes sense to us because our normal map is a two-dimensional space with three-dimensional coordinates in it. So we really want, if it's a two-dimensional space, its default normal to be pointing outwards, and any variations going to be some variation of that default normal that's pointing outwards, right? So that makes sense to us. The normal map should look like that. The only problem is these are not world coordinates. This is not world coordinate space we're working in here. This is the the map's local coordinate space, which is in UVs, it's in zeros to ones. This is not something that we're thinking of as having a relationship to our world space. So if we take these normals and we just slap them onto this triangle, we're going to get this situation. So the expected normal of the triangle is this one pointing upwards, 0, 1, 0. But the average normal from that map is 0, 0, 1. So this just happens to be pointing along the z-axis here. And so the problem we're getting here is that if we just sample those normals and just plaster them onto the triangle in some way or another, the normal is no longer coming out of the triangle. This is pointing across the triangle, which is not the worst case. If this triangle was up on the XY plane and aiming the wrong direction, the normals would be going out the back of the triangle. So if the normals are going out the back of the triangle, they're going to be negating the lighting entirely. So we're going to end up with like kind of negative normals. The dot products are never going to give us a positive value, which means our diffuse lighting will disappear and our specular lighting will disappear. Not only that, even if it was visible, the odds of us having these normals lined up properly with the surface is very, very low. It would only happen if this triangle was on the XY plane and aiming towards the z-axis. So you're talking your 1,000,000,000 to 1 chance of these normals lining up correctly. So what we're getting is a situation where it's not as easy as we expected. It's not just a simple matter of saying, let's take the normals that we've stored here, sample them, and just use them in our lighting equation. So it's a little bit sad because like the other parts of the diffuse and specular map are like, oh, you know what? We changed nothing. We literally change nothing. We literally take these color values, because they're all kind of color values, and just dump them in here and everything's fine. The downside is that normals do not act like colors. Normals have a relationship to world space. So colors have no relationship to world space. Colors are colors regardless of where they're aiming, regardless of where they're placed. Normals have a very, very important relationship with the object that they're on. So when we're calculating our normals, they come perpendicular out of the object. If we want to play around with these normals, they have to be related to this normal. So if this triangle turns, then the normal map needs to turn with it, right? So this normal map that has all my weird normals on it has to always be related to the object and has to be aiming in whichever direction the object is aiming. So we can't just say, sample the normal, just replace the ends in the equation and use it, because that means that all of our lighting is calculated only on planes that are like XY planes with the normals coming out the z-axis. And it's not 3D then. That's just 2D graphics. So if we want 3D graphics, we need these normals to be able to move around. Okay, so that's our problem. Our problem is that we have these nice normals, and we have our triangles, and we want our normals to be able to exist in the world our triangles exist in. It's not as easy as our colors where we just copied them over. The normals have to be moved into the space. I should have said transformed into the space, because that's what we're going to be using to get there. So we're going to be using a matrix transform that is going to rotate our normals into our world space. Now, we know that we don't have to do any scaling, and we kind of don't have to do any translating to get it there, because the normals are going to be mapped to fragments. So we already know where they are, because we have a relationship between where in the normal map we are in the world space. So that one's already done for us with the mapping. But the thing that is not done for us is what rotation do we need to do on this normal map to get the normals to align with this surface. So there's a fair bit of maths here, and I'm not going to go through it in detail. Let me show you the maths. there's the maths. There's a full page of maths here if you want to step through the proof. I'm not going to step through the proof, but what I want to do is explain it sufficiently so that you understand the idea of why this works, and then you can accept the proof if you want to. You know, you can always not accept the proof and then never use normal maps, but it does work, right? It's not that difficult, right? But I just want to get you as far as understanding the idea. So, the map space. We haven't ever had to think about map space before, because texture space, we're just like, oh, it's just 2D space. And we map it onto the object. But what we were doing was we were literally transforming the positions of the texels onto the surface of a triangle. Map space is more awkward because we're not just kind of translating them, we also need to rotate them. So what we have is a space here, and the way that we think of this space is that, like any three-dimensional space, it requires 3 axes to exist. So, you know, X, Y, Z, 3 axes to exist. This has 3 axes itself, and it's called tangent space, because the idea is that every surface has a tangent, right? Every surface has vectors that go, like, so if this is the surface, we have vectors that go along the surface. There's many different possible vectors that go along the surface. So if we want many different possible vectors, then we're going to need a space. So we have the tangent, which is just one chosen vector across the space, and then we have a bitangent. And in order to make a set of axes that we can use for transforms, all 3 of these axes have to be perpendicular to each other. So the easiest way we can do this is the tangent goes across the map, the bitangent goes up the map, and the normal comes off the map. And that makes sense because this is the normal that matches the surface normal in the world. So this is the map space's coordinate system, and it's reasonably simple in its own space, and it defines exactly where the normals are in its space, and also the direction that the normals are aiming relative to its space. So it has a 0, 0, 0. It has like an X, Y, Z, but they're actually, in this case, we don't want to call them X, Y, Z because we don't want to get them confused with the X, Y, Z that's in the real world. This is why texture coordinates are UV and stuff like that. So it's actually tangent, bitangent, and normal, not X, Y, Z axes. So tangent to the map, bitangent to the map, and the normal coming off the map. Right, so we're getting into a little bit of maths here, a little bit more maths than we normally would. Right, so tangent's coordinate space, sorry, the map's coordinate space, and then the world coordinate space. We're trying to figure out what the relationship is between this normal map being placed in the world on the triangle. So that every triangle that has a normal map is going to align that map with itself in the world. And we want to find out what that rotation is so that we can rotate all of these normals so they end up as world normals. We're going to go back and forth to that, to that diagram there. So we need to find the axes of the tangent space. And that's weird because I just said that this is what they are. Like the normal comes off this, and the tangent is across, and the bitangent is up the normal map. But we're no longer interested in what their coordinates are in their own space. We want to say, if this is like an object and it has its own local coordinates 0, 0, 0, that object has a transform in world space. So it has a matrix that says this is how you get yourself into world space. We want one of those for this normal map, because this normal map is literally existing somewhere in world space just on the surface of this triangle, which means if it does exist there, we can make a transform that takes it from this space to this space. So this is in the world, and this is in its own, I don't want to say normal space, that's like the real world, but it's in its own map space. That's the way I did think of that previously. So it has its map space, but we want to say, what are these 3 vectors in the real space? Well, not real space, in the world space, right? So n is easy. N we can actually do because we take the surface normal from the triangle. So we can either generate the surface normal of the triangle, or we can be given the surface normal of the triangle. Usually in this situation, we'd probably generate it because we want this to be the average normal on the triangle. So that's good. We've got one of our three axes to build the transform there. But then we need to find the tangent and the bitangent. I'm not going to go through all the maths of this, but I do want to explain some of it at least. So there is a direct relationship between what is happening in the texture coordinates in the map space and what is happening in the world coordinates of the vertices. So if I have these 3 points on the triangle, I have a UV information on this, but I also have an XYZ information on this point. Likewise this point, likewise this point. So what I can actually do is I can say that in moving from this point to this point, I have a certain change in the UVs. So it's actually, let's go back to here. We measure these as delta. The Greek symbol delta is like the symbol for change in things. So I'm going to assume that people have seen just enough maths to understand this. So the change in the UVs between these points can be measured in the same ratio as the change in the world coordinates between these points. So what we're going to get is a situation where we can say that between this point and this point, our UVs went this far. So the U's changed by this much, so the delta of the U changed this much, and the delta of the V was this much. And so the ratio of the change between the U's and the V's can be measured in world coordinates. So when the U changed this much, so this is going to be like 0.6 to 1, and this is going to be from 0 to, actually I can't remember which, I think it's the bottom left, yeah, bottom left corner is 0, 0, yeah. So the V changed from 0 to, I don't know, 0.5. I'm just making up the numbers here. But what we can see is like, this is how much this changed. And then the world coordinates went from here to here along certain axes. I cannot say what axes these are because in the world coordinates, this is going to be an arbitrary direction. This triangle could be facing in any direction. But we can build up a relationship between how much the UVs changed and how much the world coordinates changed. And using those ratios, the rate of change between those coordinates, we can then juggle this equation around until we can solve it. I think it's a simultaneous equation that we solved for the coordinates of t and b, which is the tangent and the bitangent. And then we build a set of axes that exist in world space using the tangent, the bitangent, and the surface normal, which gives us a transform for the surface space. So where that surface is in the world coordinates. It's going to be world coordinates or view coordinates as well, right? Sometimes lighting is calculated after the view transform. Sometimes it's calculated before. You can actually do it either way. I think it's easier to learn it in world, but generally when it's being done, the camera is always at 0, 0, 0 when lighting is actually being calculated, if I remember correctly. But anyway, the trick is, after we have solved this, which I'm not going to go through in great detail, like if you want to, you can step through it here. It's on Learn OpenGL. I have to admit, I have not stepped through this recently, and my linear algebra is kind of like, it's not like riding a bike. You know when they say something's just like riding a bike and you just hop back on after years and you can still do it? Linear algebra is not like that for me. So I'm not as strong with my maths. So I would have to go through in great detail and sort of map this thing out and try to figure out exactly how it works to get it going. If you want to, you can do that. If not, you can just kind of trust that the final equation is the easiest way to use this to find the tangent and the bitangent, build yourself an a set of axes in the world space that allows you to transform the surface normals to world space. So that final set of axes gives you a rotation matrix, and you apply that transform to the normals, and then the normals will be aligned with the theoretical perpendicular normal that comes out of any surface. So yeah, I'm not going to go too deep in the maths, but I want to talk about other things though. So the efficiency and the benefits of the normal mapping. You've got to look at this, and you've got to look at these maths, and you have to ask a question. If we're calculating a new set of axes for every triangle, and we're calculating a rotation transform for every triangle, and then we're rotating this normal map before we apply it, that's just a lot of extra work. We're doing a lot of extra work in our shaders to make this thing work, and the question has to be, are we getting enough value to justify that? And that question is very hard to answer because it's subjective. Because what we're asking is the difference in visual quality worth a certain cost of processing? Those are apples and oranges. You can't compare them. Right. Kind of can because they're fruit. Anyway. Just love playing around with like terms of phrase. But can you or can't you, you know? It's like, this looks cool. We should spend more processing time on it. And it's like, well, I guess so, but what if we run out? And this is the kind of thing that the hilarious thing, like when you're playing games and you turn on or off different quality settings, and you're trying to get like a certain amount of frame rate so that your animation quality is clean and then you can understand movement, but at the same time you want your visual fidelity to be as nice as you can get it. So you're always playing this kind of trade-off game between what looks nice to you, like what looks pretty to me when I'm playing my games, versus am I watching a very pretty slideshow, or am I actually seeing things animate correctly? So it's a subjective thing, but it's a decision that has to be made either way. However, I can do one better with normal mapping. I can give us a measurable increase in our in the speed that we're doing our rendering, while we are making a less of a compromise than we'd expect on our geometry. So one of the greatest things about normal mapping, and this is Hamish's question from earlier, is that we reduce the requirements for geometry detail by doing normal mapping. So if this was a much more complicated model, lots of curved surfaces, you know, lots of stuff going on, and I said, you know what, we can reduce the number of triangles on this model. We can significantly reduce the number of polys on this triangle, and instead do heaps of our curvature, heaps of our surface detail, heaps of our like battle damage, or other kind of stuff that we're going to do on the model just with a normal map. And the only processing we're going to need to do on that is some rotation and sampling of the normal map. But what we're going to do is use 10% of the triangles that we're going to do otherwise. That's an obvious benefit. We will be able to see really clearly that our frame rate will go up by doing that, because the cost of doing that transform and stuff like that is much less than the cost of processing significantly more triangles. So for significantly curved surfaces, significantly featured surfaces and things, normal mapping you can measure the benefit. So there's a cool example here. This is a hilarious example that Xavier made. This is an exercise that you can do, but I'll talk about the one on the left first. So what we do is we have this extremely high polygon model here. So this is super high polygons. We're looking at the idea of that kind of 100,000, 200,000 tries on this. I'm just guessing, ballpark figure here. The artist didn't give us any more information about it. But what they did though was they took this high polygon model and they measured all the normals and put them into a normal map. So this normal map, you can actually see it really clearly, the RGB of this normal map. So they've unwrapped it, and then they would put this into a texture, but they've unwrapped it, and you can actually see that, say, the red is the axis going out to the left, the green is the axis going above, and the um and the blue is going to the back of the face, I think, because I think we're hitting blue on either side of this. It's hard to know when something's been unwrapped where it actually ends up. So, but what we're definitely seeing is three axes of potential normals coming off this object in different directions. So, and we're getting these smooth gradations of this object over the curve of the head and things like that. But we're getting these sharper angles in here, in amongst the eyes and things, and especially you see the sharp angles in amongst the ears. The ears are separate models because ears are really complicated, but they'll be attached afterwards. So the trick is we take this, what we're looking at, I'm just going to ballpark this thing at 200,000 polys. I don't know. I'm just really guessing here. 100,000, 200,000. It's something massive. And here we're down to about, just looking at ballparking that, it's 100 polys. 100 to 200 polys. I'm just guessing, right? But the difference is stark. It's a massive difference between the number of polygons here, the number of polygons here. We take this normal map and reapply it to the low polygon object. It's kind of amazing, right? There's only a few points where we can see a significant difference between the high quality object and the low quality object. This is significantly faster to render than this. The only things you have to deal with are the corners on the head, and there's a little bit of loss of detail where the geometry can't keep up. So there's these things that look like hard edges here and here, but the normal map is dealing with all of the issues of this low polygon model and making it look like it's a much better model than it is. And look for this in games, you will see it. Because you'll see, especially on faces and things like that, you'll see, wow, that looks really good. How come that face is modeled so nicely, yet it is still working in real time? It's because it's one of these. It has a very, very low poly count, but a very, very good normal map on it. And sometimes that's all you need. The biggest clue is like, wow, facial features look really nice. Why are there angles on the top of the head? And why are there so few triangles? You know, that is a really low poly count there, but we're still getting really good surface detail. It's all based on this normal map. So normal maps are, this is what they give us. This is the capability that they give us. And this is an exercise that I think Xavier's already uploaded this. So he sent me this video and he said, hey Mark, is it okay if we use this normal map that I made for the class? And I was like, do it. This is hilarious. So this is the outcome of one of the extra exercises that Xavier's put in. So we're not necessarily doing normal maps in the tutorials because it's just too much work. We've got to do the basics in the tutorials, which is like Specular Maps. But if you want to, you can go on and do this exercise and you get this hilarious, the first minted Mark coin, physically minted Mark coin. So you can see, especially when it turns side on, that there is no geometry. It's a pretty simple, let's see if I can, yeah, there you go. Side on, perfectly flat. But at certain angles to the light, it really does look like it's embossed because it's taking the lighting equation. Actually, should probably add specular lighting to this example. So if you go ahead and do this, add some really specific specular lighting, even to the point where you don't use a spec map. So you only use the normal map and specular lighting and watch the effect that it has. Because without the spec map, the normal mapping still does amazing things for specular lighting. Alrighty. So that's where we are. Actually, we did end up using, I should trust my instincts. When I write a lecture, it's like nearly dead on 2 hours. I don't know. So what did we look at today? We looked at working with diffuse maps, and we didn't really have to look too hard at that, right? Because we know that already. We've worked with textures already. But what we did was we added the idea of specular maps, allowing partial reflectivity. And I think one of the important points that we learned today is that using maps allows us to separate objects within the object. So there's so much effort in graphics that goes into not screwing with triangles, right? It's just like, this is the thing that we count for the thing that's going to cost us the most in processing is the number of triangles. So if we can not have to add triangles just to add features, then we will do it. You know, we will reduce the number of polygons as much as we possibly can. So specular maps allow us to say, all right, this one object has metal and other materials. So instead of needing separate materials on the object, we just go, nah, some of this uses these materials, some of this doesn't, but I shouldn't use the word materials. Surface properties, because materials are keyword. But you know, some of this is metal, some of this is leather, some of this is wood, some of this is skin, some of this is plants, you know, or other materials. Some of this is plastic, you know, and each of it's going to be a little bit different. But what we can do is just use the map to represent that difference. So, particularly objects that have different reflectivity of light, that's where a specular map allows us to do that. And then the other thing about reducing the number of triangles we're going to need by using surface materials is like, what if this thing has a super detailed surface? So what if I'm doing, I think the classic one is like, what if I'm doing steel decking on like a boat or like, or even just on a ladder or something like that, and it has all those embossed little bits of metal. It's like, what if I want to do that, but I don't want to model that because there's so much geometry in that. I wonder if I can. I'm looking for something different that has less geometry. Oh, it doesn't matter. I won't. I won't bother looking stuff up. Right. But if we have that, we can mimic surface geometry without having to actually create it. And if we want to, we can do this kind of thing where we can actually create the geometry and then optimize it after the fact. And that totally works, right? So we can grab the normals from the complicated model, optimize it after the fact, and then we've got this real-time compromise model, which is a pretty good compromise because there's only a few parts of this that give away the low poly count. We still get a lot of this nice surface detail there. So what we're doing basically, the whole idea with maps, from the basic textures that I showed you at the beginning through specular maps to normal maps, the whole idea that we're doing, we're getting at with this is that we want to do the most we can without adding triangles to things. And so that's what this is all about. All right, I'll wrap it up there. I'll go into be right back mode and I'll come back afterwards and answer any questions anyone might have. If you have any questions, you want to know more about any of this stuff, you want me to talk through more stuff, put your questions in chat now and I'll come back afterwards and answer them. Hello, I'm back. It doesn't look like there's any questions today. That's all right. I mean, when you go to tutorials, you can work through the specular maps and things like that and get an idea about how to do these things. If you're going to go on and try normal maps, I think that's the kind of thing where like what I'm doing is any of the advanced stuff that I'm talking about here, I'm probably going to reserve that for assignment 3 and give you marks for going beyond what we've explicitly taught you in the tutorials and being able to expand them further. So Hamish, I hope that answers your question. Can artists convert a 3D model to a flat model with a normal map? The answer was definitely yes. I mean, it depends how flat you want that to be. So this one here, I mean, it's not entirely flat. This one is entirely flat. But I don't know how Xavier generated the normals for this. I don't know if he was using some um, kind of method of taking the contrast in the original image and assuming shadows in some places and assuming light in other places, and then creating the normal map from that. But this one's definitely high detailed image with lots and lots of triangles, which means that with all of those triangles and interpolating between the normals on all the verts here, we can create this smooth gradation normal map. And then we lose our smoothness by taking out a whole lot of the triangles, and we kind of reintroduce the smoothness of this model by putting the normals back into place. So the process of lowering the polygon count, optimizing this model, puts all of the triangles on this model into this map somewhere, because the new triangles that do this are often sharing vertices with the old triangles here, which means they can take the texture coordinates from these triangles and still map into this space here. One of the simplest forms of polygon optimization is to find find vertices that exist in between other vertices and just take them out, and expect the model to just kind of survive that. It's not that simple, right? There's an algorithm to make sure you don't take out vertices that are crucial, and you don't take out vertices so that triangles don't appear anymore and stuff like that. But there's a lot of algorithms that exist in 3D art programs that can do this, that can take this to this. I think this is a ZBrush kind of thing, so a digital sculpting thing, and then ZBrush can then lower the poly count on things. This is really aggressive, lowering the poly count as much as it is here. Yeah. Jason saying parallax mapping solves the problem from Genshin. Yeah. So, depends which problem. The problem of um the flagstone or cobblestone not obscuring my feet in Genshin, that can't be solved with parallax mapping. But parallax mapping is normal mapping taken to the next level. So parallax mapping is normal mapping, and it's more than just having the normal so that the lighting changes. It's not a lighting mapping technique. It's actually a visibility mapping technique. So let me show you. I didn't do this because I knew that we wouldn't have time to cover it in detail. But if you wanted to look at it, parallax mapping adds on this new idea that some parts of this texture surface, I shouldn't call it texture because that's a keyword again. Some parts of this surface can obscure other parts of this surface because this is a simulation of things with depth. So it has no real depth, but it's a simulation of things with depth, which means that the normal mapping is going to give us this lighting in between the objects. The parallax mapping is going to give us a look so that these things are actually appear to be popping out of the surface, because parallax is the idea that when we look at something, we see the front of it, we don't see the back of it, but objects appear skewed to us if they're in a different kind of alignment to the angle we're looking at it. So if we're looking at this surface and it's flat, we will never really see the inside edge of this, and we won't have the outside edge obscured if this thing is flat. But what we can do is we can measure the angle of the eye onto the object and say, because the eye angle on the object is looking upwards in this area, we will see the bottom edges of these bricks. Because we're looking down on it from the top, we'll see the top edges of these bricks, and so it gets this kind of thing, and it recalculates what we see of an object based on the angle we're viewing the object. I didn't go through it because it's reasonably involved and reasonably complicated. But yeah, so normal mapping, the object kind of looks flat. Parallax mapping, it gives us a view onto the object from our eye position specifically. So the normal mapping doesn't calculate based on our eye position whether we see or don't see parts of it. So it just plays around with the lighting. Whereas parallax mapping plays around not just with the lighting, but with the visibility of different parts of the object. And it really, really gives the idea that something is popping out off the surface, which is exactly what was happening in Genshin. So my assumption is what was happening in Genshin was definitely parallax mapping, but can't be 100% sure on that. But my assumption definitely is that. Okay, I don't think we have any other questions here. So I might wrap it up there. Thank you all. We now are at a point where lectures wise, there's nothing more that you need for assignment 2. Tutorials wise, this week is still definitely tutorial worth going to for assignment 2, because it will teach you about specular mapping, which is one of the requirements of the assignment. Okay, I'll wrap it up there. Thank you all. Have a good week, and I will see you next Monday. Next Monday, we're going to go into this very interesting little world, talking about reflections, where we're not just simulating the reflection of a light source, but we're going to be able to see reflections of a scene in an object. Okay, see you later.